last speaker before lunch is Sandeep Pradhan, and he's going to tell us about Lossy quantum source coding with global error criterion. Please take it.
So thank you for organizing this nice conference and this joint board with my students, Tawhid and Mohammed. And let me get to the problem, starting with quantum source coding in the asymptotic setting. So we have a quantum source which is modeled as a density operator, and this is a pretty standard problem. So there is an encoder which works on n copies of the source, and there's a decoder which is going to do the decompression, and want the reconstruction to be close to the original in the almost lossless setting. And this was addressed by Schumacher. And here is the kind of the situation. So we have the source, and this is our reference to the source. So we have encoding CPTP maps, and this is the decoding CPTP map, and M is the message that is being sent. And this is the joint reconstruction and the reference state. And N is the blocker. And we have a global error criterion, block error criterion, which is that the original source along with the reference should be close to the encoded state, encoded and decoded state. And here I'm going to use Bob to do the encoding, Alice to do the decoding. And the range here is given by the 1 by log the dimension of the states, and want to find the asymptotic performance limit. And the theorem is that reliable compression is possible but only if the rate is larger than the quantum entropy of the source. So the question is, if we go to lossy compression, so what can we do? So one simple idea that we can think of is that, well, if we have this relax this assumption and then say that we have the global error criterion, which is epsilon, so can we have an R epsilon trade-off? Because I want to come below entropy now because I may not have enough resources to store the data. But we have a no-go theorem, strong converse, which says that if the rate is less than entropy, then the probability or the distance, error distance, goes to 1 asymptotic exponentially fast. So there is nothing much you can do, and this is also a similar behavior that is observed in classical. You see that if the rate is less than entropy, then this probability of error approaches 1 exponentially fast. So then we kind of look at what Shannon did in the classical. So what Shannon did was that he formulated an optimistic formulation. So we have an IID source which is given by some distribution. So he came up with this idea of a bounded distortion function. So we want to model loss through a distortion function. And then we look at this local error criterion, which is the average of the distortion of each sample. Right? So this is like, information theory 101. And we say the rate, R&D rate and distortion are achievable if there is a compression code such that the average distortion between the source and its construction is close to D. And we have Shannon came with the singlet characterization, which is given by which information, where we minimize which information overall forward transformations, what we call forward test channel. The all transformation exact given x is the source, exact is the construction, so exact is the distortion function. And by having this distortion criterion, we are able to come below entropy because now we have mutual information. And this is a singlet characterization, so asymptotic setting and singlet characterization. Now we need something similar for the quantum case, and this was done by Barnum, analogous to this. And Barnum came up with this notion of distortion, which is average singleton distortion. When he looked at the 1 minus the entanglement fidelity of any source with which passes through a channel, and he introduced the unrelated distortion as the average of singleton, like a local distortion. Right? So this is where so if you look at the original the source, I copy of the source and look at its corresponding reconstruction, which is obtained by this big object here, which is the encoded and decoded source, and then you partialize everything except the ith sample. and you compare with how that here it is. So what we have is that the distortion here, rho and fn of I, is the corresponding the ith sample what's happening. So local error criterion, and so this was done by Barnum, and then what we I can't even move forward and backward.
Maybe you can try to fix it, or maybe you can continue with touching the laptop.
Okay, so this is the Barnum's distortion network. And what we have is a pictorial representation here, where we have n copies of the source, the corresponding the references are going like that. The sources are encoded in blocks of length, and there is going to be a decoder, and we measure the average distortion rate.
Sorry, I think you have to continue like that. This doesn't seem to be working.
Okay, that's okay. And so there are several results available in this setting. So first is the quantum classical setting, and this was solved with Datta et al., where we have a singularity characterization. And also in the fully quantum case, with the entanglement assistance, with unlimited entanglement, we have the distortion function, which is again given in terms of singularity characterization. But in the unassisted case, so this is a quantum lossy compression with local error criterion, with fidelity criterion, for example, we have this expression for the performance limit, which is a regularized expression expressed in terms of entanglement of purification. So this is a double minimization because this minimization over forward channels, and then in the entanglement purification, we still have to do one more minimization inside. Okay, so this is a N-letter object, and so there is so we don't have a single characterization. So okay, so we were thinking about this problem, and we were thinking like, can we have an alternative formulation? So note that information theory stands on two pillars: the channel coding and source coding, packing and covering. And if you look at the quantum channel coding, we have the performance limit again written in terms of the regulated expressions, but the performance limit is given by coherent information. But we don't see that here in the source coding problem. And we see that there is a strong duality between source coding and channel coding. In fact, the problem of packing and covering has been studied even before Shannon. And I was, if I recommend you a book by Rogers, which is again packing and covering studied in the math literature, where the notion of duality exists even beyond Shannon. So the duality is a very strong kind of notion that connects packing and covering. And in quantum error correction course, we see that it is actually packing of subspaces. So quantum source coding must be covering of subspaces. So for example, if you think of covering, suppose you want to quantize something of cover. Basically, suppose this is the kind of the source, and you have these reconstructions. Now, given the reconstruction, you look at what is the distribution of the source. It should be kind of close to being on the surface of the sphere, right? So it's like a basic idea. So that is the kind of the motivation for us, where we want to formalize this notion and say that given the reconstruction, how does the source look like? Right? Given the how does the source look like? So in the case of quantum, we don't have access to the source, so we're going to be looking at how does the reference of the source look like. But we go back to classical and do some homework. So if you look at the Shannon's formulation, it's a minimization over forward test channel. But actually, if you see the literature, the reverse test channel, what's called the backward test channel, plays a much more significant role. So what is the backward test channel? The backward test channel, how does the source look like given the reconstruction? So it is the distribution of the source x given x hat. And it has very interesting properties. For example, it is unique, although the forward optimization, the forward test channel may not be optimum, like it may not be unique in terms of the performance, the minimization, but because you can show that the reverse is unique. And it's also the posterior probability distribution from a Bayesian perspective. And it is used heavily in estimation in detection. So we were asking, hey, what is really going on in a rate distortion achieving curve? Right? because it achieves the distortion. But what is really going on there? So let's look at it again. So we are taking an IID source. So we have IID source is the product source. And the reconstruction is, so we are, since we are doing an encoding in blocks of like that, there is no IIDness for the reconstruction. It's not IID. So joint distribution is not IID. But what is any IIDness there, right? Beyond just the IIDness of the source. So here is the source. This is this should be encoder decoder followed by the encoder. It's like that here. So this is our system, right? So source and it's encoded decoded. But we can look at from a Bayesian perspective, given the reconstruction, what is the distribution of the source, right? We can always do that decomposition. And we showed, long time back, that for any rate distortion achieving curve, it's one of the interesting properties. For any rate distortion achieving course, we see that the reverse distribution, that's the Bayesian, the posterior distribution of the source given the reconstruction, looks like a product, which you would expect, because if you're doing a nice packing, sphere packing, and if you see the reconstruction, how does the source look like? It should be on the surface of the sphere. So that means it's like a IID-ness kind of built in. So this is the motivation for reformulating the last sodium form. So the idea is that any rate distortion achieving code, this actually happens. That means the reverse test channel, the unrelated reverse test channel looks like a product, looks like distinct numbers. And we showed this closeness and relativity, normalized. So why not take this as the motivation for formulating a new source code? So as I said, this is the combining all these observations. So we want to formulate with a global error field based on the backward test channel instead of a distortion function. Now there won't be any distortion function, but I'm going to use a channel to measure the loss in the reconstruction. And for information theory people like us, what can be more information theory than a channel? Right? So any loss function, it's you can hardly, sometimes argue that it's not information theoretic, but nobody can argue that channel is not information theoretic. So channel is the most information theoretic object, right? So I'm going to use a channel to model the loss. So here is the idea. So this is I'm talking here classically. So I'm going to now specify, hey, my reconstruction, my source has to look like this given the reconstruction. So that's my the formulation. So I'm going to specify, instead of a distortion function, I'm going to specify a channel that models the loss. Okay, so more noise in the channel, the lossier the reconstruction. I find so the object condition of finite codes, encoder and decoder, such that this is the system, the source and the encoder decoder system, that should look like this. This is the reconstruction, can't change that. But we can ask, how does the source look like given the reconstruction? This is the distribution of the unrelated source given the reconstruction. I want it to look like a product. Let's say put W to the power n. So given the reconstruction, the source has to look II. And we formulated this and we found that the classical case, in the quantum classical case, the performance limit is given by which information. Okay? So now the question is, can we do this on the quantum, fully quantum? So again, recall that this is the problem formulation in the classical system. So you have the source, you do the encoding and decoding, and but it has to look like this. As much IIDness as possible. Also, the confidence is beyond IID, but I'm looking at IID. So now, in the quantum case, what shall we do? So here is the quantum case. So here is the problem formulation, like toward the problem formulation. So I have the source. Here is the source. It is here. This is the reference. I do the encoding and decoding. I want to compress it so that the dimension of M is as small as possible. I want the system, which is the output, should look like this. Okay, so what does that mean? It means that if you look at the reconstruction here, this is the reconstruction, this is the reference. If you look at its purification, the purification of the reconstruction. So this is the, so again, this is the ground. It's okay. So here is the reconstruction and its purification. So we want to look at its purification. And the question is what purification? So we are going to go with the canonical purification or the what's called as the petticoat purification. And we ask, how does the source reconstruction looks like from that reference? Right? So, and it should look like it has been passed through a product channel. Right? So again, I want to make sure everybody understands it is a proper formulation. So we do the encoding and decoding like as business as usual, but the criterion is different. The criterion is that if you look at the reconstruction and look at its purification, how does the purification of the source related to that? Because I produce some loss and I want this loss to be controlled. So that's what I said. So this is the first term is the power, and this is the second term. It should look like the channel should look like it. And we have the reliability criterion, which is given by L1, and now we want to formulate the form. Okay. So construct the encoder and decoder, and we want to achieve the simulator performance. So with all of the homework, now I'm ready to see tell you the problem formula. So we are given a source, a row, which with Bob. Alice has a reconstruction report space, and the loss is given characterized through a channel NW, which is actually a channel from the reference of the reconstruction to reference of the source. So we want to have a protocol, N theta Lossy protocol, where the encoding and decoding happens. Theta is the size of the dimension, and we want to find the minimum compression rate. So we say R is achievable if for all the pretty standard stuff for all epsilon and for all sufficiently large, we want the rate to be going toward ray R, and this the L1 distance, which is a measure of lossless, should be close to zeta. So in the usual channel sense, and our objective is to construct black encoders and get the performance. And here is our result. So this is a simulated characterization with the asymptotic set. So it says that given a source, reconstruction into a standard channel, which measures the loss, rate R is achievable if and only if two criteria. R has to be greater than coherent information. We all like coherent information. Who doesn't like coherent information, right? So it's a coherent information of the reverse channel. So remember, NW is what we call a backward channel, posterior channel, which takes the reference of the reconstruction to reference of the source. So it's the coherent information of that, and minimize over all input distributions. That results in a correct reference, because note that we cannot change the reference. Reference is fixed, because nobody has access to reference. So this set S is the whole input reference, the reference of the reconstruction that gives the correct reference under the chain. It's a singleton category. Okay, so it's a minimization of coherent information. Minimization over what? All those reconstructions that are consistent with that, because you need to have at least one reconstruction that will give you a correct output, which is the rule. And actually, in fact, Barlow conjectured that the coherent information is the performance limit, but he said that it's the coherent information of the forward channel. But it turns out nature has its own thing, and it is the reverse channel. It's the first thing. Second thing is we were initially hard to believe that this is actually true, because we know that we don't have a similar categorization to the channel coding problem. But fortunately, nature is kind to us, and we are able to show a similar patterns. So for future convenience, I want to give some interpretation and try to give you a proof of this. I guess I started a few minutes late, so I should take a couple of minutes. Sorry about that. I'm going to stand between you and your lunch. So for future convenience, I'm going to use W to denote the Steinfeld extension of the chain. A Steinfeld extension. Before that, any questions here about the problem formulation? Well, it's in channel simulation, you want the entire thing to be product, right? In channel simulation, for example, if you look at Cuff's work, you want the reconstruction and the source to be product. So here we are not saying that, it's a weaker constraint. Okay, so source is product, the everything, the reconstruction is non-product, but the source has to, the reference of the source has to look product given the reference of the. All right, so as I said, I want to interpret this before I give you a proof. So first of all, let's do the duality check. And as I said, duality is the most enduring principle that has been ascribed even before Shannon. So we have the minimization of correct information. There is a channel coding problem. We have the maximization of correct information. But for some reason of for the quirkiness of our nature, there is no simulated characterization. Okay, in channel coding problem. But fortunately, we have. The second is the idea of covering. I like the idea of covering and packing. So this is the system. This is a single letter system that we want to mimic. So again, note that this is the row A is the reconstruction, and row AR is the reference. And it's going to go through that channel, and W is the time string extension. So BR is the reference of Bob, and E is this additional auxiliary state. So if you look at coherent information, it's actually, it's the entropy difference of two entropies of the forward and the complementary channels. And we can now interpret this as covering of subspace. So if you don't do any loss, then what is the dimension of the source? That's roughly 2 times the entropy, right? So let's say you need entropy amount of qubits. But now we are covering this subspace with subspace balls of dimension roughly 2 times SFU. So it's this entropy minus that entropy. Okay. However, to prove this, so we want to come up with an achievability scale, and we want to know what achievability scale should we use. So now, if you see again in channel coding, the encoder is pretty simple, and a lot of work has to be done in the decoder because decoder has to decode the information. And we see that in channel coding there are two approaches. One is randomly, but then you show the decoupling. So that means you don't really worry about the actual construction of an encoder because you show the existence. There exists an encoder. So if you decouple, that's done. But in source coding, you want the encoder. Encoder is like a decoder because Bob has to do a lot of work because he has to compress. So I don't know what decoder to use. We were not sure what to do. And then that's why we went with this Developx approach, if you see. And Developx gives Developx approach to channel coding. He showed the capacity for the first time. And he used a very explicit encoder and decoder, okay, which is based on this another interpretation of coding information, which is the difference of level coordinates. Okay, so this is a difference of level coordinates, and there is a nice connection here to all kinds of things that happens in this issue. So I'm going to give you a brief idea as to how the coding works. Okay, and I'm going to have to skip a few slides here. So this is the problem. This is what we want to accomplish with representation, and we are given that situation. So I'm going to tell you a brief idea as to how the encoding and decoding works. So we start with that situation. So we are given some optimization, which is the minimum of coordinate information overall row AR. So choose an arbitrary row AR. This is row AR which belongs to that side. Now the question is, I need an encoder. So here is the simulator system. It says that this is what enters into the optimization, simulator optimization. But I need to construct an encoder. So this is the reverse channel, the backward channel. Now we come up with this idea of a posterior reference map, which is basically inverting that channel. So the idea is, so again, look at this. So this is OA is the reconstruction, and that's the reference, and then passing through a channel. We know that that's a pure state. We are ENA, that's a pure state. So, and we can also think of a pure canonical unification of Bob's reference, which is Bob's source. So there is a canonical unification. It's a pure state. And both are unifications of rho BR. So that means there must exist an isometry that connects the Bob's source with any. It's what we call a posterior reference map. It's like basically involving the channel, so push the channel to the other side. And you can do this according to the deal with a canonical fluidity, which is pretty good fluid. So I push this W which is sitting in the reference to downstairs where we live, and then we have the V. Now I'm going to use some little tricks here to come up with an encoder which is based on this V. So V is like a forward transform. Yeah. So so I'm going to skip this part here. So what is the idea? So as I said, when we were trying to prove this, we had two approaches. One is the randomity, but we didn't know how to deal with it because there's no explicit characterization of the decoder, which we needed it. So we followed this approach. So for that, we need to use the idea of measurement, because what system should we use? So we use the idea of coherent measurement. Okay, because there's already been work done by Winter on measurement compression. So question, can we use a coherent version of that measurement to come up with the electrode? All right, so I have 3 minutes, and here is so this is the idea of coherent measurement, which is pretty standard in quantum information theory. So it's like it's going to be like so you keep all the outcome of the measurement in a coherent superposition. And so this is our system. So the system that I showed, the blue system, which is I tensor V acting on the source. And if you do a little bit of manipulation, we'll just insert a complete basis and do some little manipulation. You get you can write that as a coherent measurement. Okay, so you get a measurement, which is what we call MA, and this MA can be written like that, which is so we can get a measurement. And so we do now measurement compression, but not coherently. Okay? And now do that because Winter has done this in the non-coherent setting. So that's the Winter's measurement compression. And Winter shows that you can do close measurement compression in that way, which is the first coherent, Hollywood quantity. We have difference of Hollywood quantities, so at least we try to get the first Hollywood quantity. And this is the fundamental connection between coherent information and Hollywood quantities, which is also exploited by Develop. And as I said, Winter's approach was non-coherent because it was a quantum classical system, so we want to keep it in a coherent superposition. And in the process, we need some lemma. Again, due to lack of time, I'm going to skip this. So essentially, so with some additional rotation unitaries, what I can show you is that we can accomplish what we want, and we get the storage rate, which is given by the Hollywood quantity. Okay. So remember, the coherent information is difference of Hollywood quantity. I want to achieve difference. Okay. I at least achieve the first quantity, which is the first Hollywood quantity. Yes. Now, how do we achieve the second? How do I? It pays to be greedy in information group, right? So I'm kind of greedy now. I want to reduce the rate even further. How can I reduce the rate? Because there's already everything superposition. But note here that when I do coherent information, so I'm going to go back to this picture here. So look at this kind of picture. So what happens is that this is the single letter system which I want to mimic in N letter. So I do some N letter coding, and then produce the this A, which is the reconstruction. But there is some residual quantum state that's going to remain, because in a coherent measurement, you have the measurement acts on the system, and then you produce something else, and that's the reconstruction. But we have the post-measure state. What do you do with this? Right? So you did the measurement, and in the measurement, you get an outcome, you send it. And in a coherent superposition, you send the qubits. But what do you do with the post-measure state? I need someone get rid of it. Okay? And I can't simply get rid of it just like that, because it destroys superposition. So there's one more nice thing you can do. So which is basically, I'm going to say here, the last slide here, which is basically I do a measurement, one more measurement. And the idea is very simple. See, you do the measurement, you have this post-measurement state and the measurement outcome. They're all in coherent superposition. Okay? But it turns out there is still some redundancy. Okay, so I don't have time to go through that. There is still some redundancy there. Nature preserves some more redundancy. Okay, So what I'm going to do is I'm going to do one more measurement in a coherent way, remove that redundancy. Okay, remove that redundancy, and I'm going to dump the post-measured state because now it's useless for me. Because I have to dump it, I can only send the part of the information. And this extra information that I get is precisely this additional coherent information, which is kind of, it has a very nice interpretation regarding treating the post-measured state as identity. Okay, so with that we get the achievability. I don't have time to go through the converse. But one might question here, hey, well, I mean, this is your formulation. What is the big deal here? Is it, anyway related to anything fundamental? It turns out from this, so we did some more joint work with Andreas Winter. He's one of he's a committee member for my students. So we started discussing, and we now have much more wider connection of this problem to other problems. For example, one-shot quantum soft covering. And nobody can argue that that is a concurrent problem. It's a very fundamental problem. And we are able to show again the performance, which again is given by coherent information. It turns out we can also relate this this posterior reference map with the patch recovery. They are at least they are very similar. Also, there is connection can resolve ability, quantum ability, and also the identification by. I think with that, let me stop. Thank you very much.
Yeah, maybe I just got confused during the presentation, but did you change the problem slightly, or it's still the original?
There is no distortion criterion. We have a channel to measure the loss.
Yeah, so you change the problem, but classically they would be equivalent.
Classically, they are the same. Classically, the soft covering, this formulation, and the Shannon's formulation, they all give the same rich information. But in quantum, the soft covering, which is basically a quantum version of covering lemma, for example, Wills book, and this, they both give coherent information, but the distortion formulation is not.
One last further quick question. Yeah, sure.
So, I mean, this is really nice. I mean, these things that appeared in the classical information theory literature as tricks, right? You're trying to solve a source coding problem, and instead you're going to use sort of channel coding primitives, or you want to solve the channel coding problem and you use binning, right? Source coding primitive. But it's the first time I see a situation where you seem to need to do it to get to where.
Well, it's also used by Devatak, I should point out.
Right. I mean, these things have been around, but I don't think, I had seen a situation like the direct source coding way, trying to fill in the entropies that create doesn't.
Right, yeah, I mean, we were initially struggling as to what approach should we use, as I said, that there were two approaches. One is random entry, but we don't know what the decoder is, how the decoder looks like because of the existence of a decoder. But we need that to do the compression. But now with further discussions and further work, we are actually able to do that in a one-shot setting. So this is our recent work where we are able to get the one-shot version of this, but now much simpler proof. But it is an existence kind of a situation.
Okay, there are no further questions. Let's thank you.